All right, there we go. Sorry about that. That should be corrected now online. Anyway, the way that we went about doing it last time was using recursion, and recursion is nothing more than a function calling itself. So let's walk through this as a review here. We're calling this function called countdown starting at 10. We pass in 10. And if we've gone down to 0, that's when we print blast off and we simply return from the function. Otherwise, if it is greater than 10, else, right, then we print out whatever the number is and then call the function and decrement I. So instead of writing our own loop to do all this, what we've done, it's still screwed up. Oh, okay. Good enough, I guess. I don't know why it's not working like this, but there we go. I don't know. Anyway, that should be fixed. The video was not good online. Anyway, we call countdown here on I minus 1. Now, what I wanted to do first, as part of this review of what we covered last time, is to visualize this. How is it actually doing this loop? It's exploiting the call stack. As I walk through this, you'll see that we call countdown 10 times. Initially, we call it with 10, right? And then when we make that recursive call after we print it, right, we're going to call countdown and pass it in 9. Right? So you can see this pattern. What's going to happen here is that every time we call function, function calls function calls function, you're going to have a stack frame with all those variables. So instead of a traditional loop where you have one variable that can change and go from 10 down to 0, you now have 10 variables, one for each value, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Right? You'll actually have 11, I guess, right? As we get down here to the very end, 2, 1, 0, right? So we've got like 11 stack frames here for countdown. We're abusing the call stack to be able to do this, right? And that has consequences. As we saw last time, that if we call countdown with a bad value, say -10, right, and compile this, what's going to happen here? Is it ever going to get to this termination condition here where we've got 0? Nope. It'll just go -10, -11, -12, right? And so do we have an infinite recursion? Well, if we had an infinite stack, we would have an infinite recursion. We don't have an infinite stack. Eventually, your stack will get full, and then the next function call that you try to make, guess what happens? Overflow, stack overflow. Let me make sure that this is actually working. Yeah, okay, good. All right, so I wanted to cover this in a little bit more detail here. Before we do that, though, that was kind of a toy example, but it's actually not a toy example when you consider some other programming language paradigms, like, for example, Haskell or any Lisp or any functional programming language. You have many functional programming languages that don't even have loops. You're supposed to use recursion as your de facto control structure. And there are various good things about that. There are various bad things about that, right? So what is recursion in itself? It's something that self-references itself. In coding, that means a function that calls itself one or more times. Right? What about in mathematics? Where have you seen maybe cool art projects in mathematics? Self-reference or self-reflection or or recursion?
Imaginary numbers thing. I don't know what it's called, but like zoom in.
Fractals. There's the key word. Fractals, right? If we look up images of fractals, these are self-similar objects, right? One easy one to visualize is the Sierpinski triangle. I don't know if that's spelled correctly or not, but it'll come up anyway, right? Here's an image of the Sierpinski triangle. How is it built? You start with a triangle, and then you cut out a triangle in the center. And then you recurse and repeat that on the 3 remaining triangles. And then you do that again and again and again, infinitely, right? And that forms a fractal, right? There's the Sierpinski triangle. There's a Sierpinski triangle in 3 dimensions, 4 dimensions, etc. What you mostly saw, though, is the Mandelbrot set, because nobody wants to look at triangles. All of these are probably just iterations of some Mandelbrot set, which has a different mathematical definition. But it's self-similar, because as you said, if you zoom in on it, it will look the same, right? If you infinitely zoom in on it, then it will infinitely look exactly the same because the definition is infinite. It's always recursive, okay? All right, so how do we write our own recursion in mathematics? Again, mathematics, you have, in coding, excuse me, you have self-similar objects. And the de facto example that always comes with recursion is the Fibonacci sequence. And I'm not going to do it any different. I am going to give you the Fibonacci sequence, and we're going to do that as the prime example. But I'm going to do it with a little bit of a difference in that this is a perfect bad example, right? This is exactly why you don't want to use recursion in practice. Because it's a perfect bad example because it shows you exactly the disadvantages of recursion. And we'll see that here in a second. I don't want to have to copy all the math, so here we go. Right? Here's the Fibonacci sequence defined in math. Right? So if it's a sequence, so we have n here. If n is 1, then it starts out at 1. If n is 2, then the second value in the sequence is 2. So let's write down the sequence here to remind ourselves of what the Fibonacci sequence looks like. So 1 and 1 are the first two values. Now, what this does is, as you get beyond the first two values, those are called the base cases. As you get beyond those two values, the next value is the sum of the two previous values. So now that we have two previous values of 1 and 1, then the sum of those is 2. The next one will be 2 and the previous one, which is 1, so 3. Right? What else? 5, 8, 13, 21, 34, and I'm writing all these out so that we have something to test with as well, ... right? It's going to go on infinitely, right? This is going to grow exponentially as well. In fact, you can solve for this and come up with a base of the golden ratio and such, whatever. The Fibonacci sequence is way overrated. It is nothing more than a linear homogeneous recurrence relation of degree 2. Those are a dime a dozen, right? Why the Fibonacci sequence is so mystical, or the golden ratio or whatever, it's because people attribute meaning to it where there's not really meaning there, right? But it is a basic sequence that we can start to design our own recursive function for it. How do we go about doing that, right? Well, if recursion is kind of a faking of a loop, then you have the same three basic control structures as a loop. With a loop, you have an initial condition, you have a continuation or a termination condition where you don't loop anymore, and then 3, you would make progress towards that termination condition. Likewise, every recursive function needs one or more base cases, right? These are termination conditions in which no further recursion is performed. Right? Our base case over here for the countdown was when we hit 0. If we didn't have that base case, if I got rid of this entirely and we just printed it out and then counted down, we would get into an infinite recursion and eventually a stack overflow. Just like if you didn't have a termination condition in your loop, you would have an infinite loop. Right? Some base cases may perform basic error handling or corner cases. For example, we didn't take care of that over here with our demo. Let's do that now. Right? I'm only ever going to count down from, say, 10, 9, 8, 7, 6, 4, 3, 2, 1. I'm not going to count down from -5 down to count up from -5 to 0. So let's go ahead and take care of that as a base case. If I is less than 0, then we'll go ahead and print an error message, or actually we'll just go ahead and return, right? We won't do anything. We won't even bother to print anything. And by the way, that is a continuing problem that we've seen in some hacks. When you do error handling, you simply return. You don't print anything, right? Don't print anything to the standard output, because in a real program, nobody's sitting there staring at the screen 24/7 looking for a basic error output, right? In a real program. So if it's out of bounds, if it's an error condition, we're not going to do anything. We're just going to simply return. Otherwise, we'll print blast off and then return. Otherwise, we'll go ahead and do this countdown. So this is a base case, or this is an error handling base case, or a corner case. Right? And now we've got two base cases. Right? Otherwise, you make one or more recursive calls to the same function. making sure to make progress toward one or more of your base cases. Right? And again, what would that look like if we didn't? Right? If I simply just called countdown on the same variable here, countdown of I, countdown of I, countdown of I, countdown of I, are you ever going to hit 0? No. So you have to make some sort of progress towards your termination condition, just like a loop. Otherwise, again, you have an infinite loop, an infinite recursion, Stack Overflow. Okay? And then, of course, the initial call to your recursive function is your initialization. Initialization statement. Right? Int I equals 0, that's where you start a loop typically. Well, when you call the function, you need to give it its initial seed value here. Here, I'm calling countdown from 10, right? Or if I wanted to start the countdown at 5 instead, or 3, 2, 1, right? However short shrift you want to give somebody, right? Okay, so with that in mind, help me out by writing a recursive function for the Fibonacci sequence here, okay? To do that, I'm going to go ahead and get rid of this artificial countdown function here. And let's go ahead and create a variable n here. And I want to compute the nth Fibonacci number. Let's go ahead and go with the 10th Fibonacci number. This will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it should be 55, right? I'm going to expect 55 if I'm computing the 10th Fibonacci number. Sometimes the Fibonacci sequence starts at index 0, so you may be off by 1. It all depends on what your definition is. But here, I'm using this definition where we start at 1. It's not defined for 0 or less than. Right? So help me out. What should I call this function, first of all? Fibonacci? That's not the guy's name either. It's something Nazi. It's something completely different, but 300, 400 years ago, they named him after the place that he was from, too, or his father or something. What is it? Okay, Bonaccio or something like that. Something Italian, right? Maybe. I don't know. All right, so Fibonacci. What am I going to take as input here? Int n, right? The nth Fibonacci number. What am I going to return as a return value here? These all look like what to me? Integers. So we could return an integer, but actually, remember that this is going to grow very, very, very quickly. So I'm going to go ahead and return a long. Remember that a long is a 64-bit integer. We don't usually use them here, but I'm going to use that for this demonstration because I want to represent larger numbers, not just the small numbers. Okay? All right. What do I do first when I design a recursive function? The base cases. Let's take care of the corner cases, the error handling cases. Is the Fibonacci sequence defined for 0 or negative numbers? No. So let's go ahead and take care of that. If n is less than or equal to 0, this is an error. Should I exit? Do we exit as proper error handling? Nope. Do we print f the world is ending? Right? Do we print anything as part of actual error handling? No. Right? Instead, we go ahead and return some flag value indicating you asked for the wrong thing, buddy. Right? What's a good flag value in this case? Negative 1, okay. Or 0. I like either one of those. Right? It returns a negative 1, and then we put that into the documentation. Returns negative 1 for any invalid values, and now you know how to check whether or not there was an error in the function. Okay? Else if, what's another base case here that we do, that it's not an error condition? Well, as defined over here, what are our base cases? N is 1 or n is 2? Okay? Oops. So if n is equal to 1 or if n is equal to 2, we'll return 1. Right? Remember that it's going to, the value here is 1 if n is 1, 1 if n is 2, the first two values in the sequence here, 1 and 1. Right? Otherwise, we need to make one or more recursive calls to the same function, but we also need to make progress towards one of these terminating conditions up here. And that's simply going to be Fibonacci of n minus 1, add that to Fibonacci of n minus 2. So return Fibonacci of n minus 1 plus Fibonacci of n minus 2. There we go. Now, an advocate or an enthusiast or whatever of recursion would say, wow, look at that. Really simple code, right? One person's simple code is another person's complex code. That's not really an objective measure of whether or not this is a good algorithm, right? Yeah?
So, just as far as recursion goes, I just look at this and I'm just wondering, like you could do all of this in a loop, so what makes this better than using a loop, or is there a reason you would use this instead of using a loop?
I would concur. There is no reason to do this. In fact, if you're doing the Fibonacci sequence, you definitely don't do it this way, and we're going to find out why really soon, why you don't do it this way. Recursion is used in a lot of backtracking algorithms or divide and conquer kind of style algorithms. For example, we'll get into searching and sorting here after recursion, but a common sorting algorithm is quicksort or merge sort. Both of those are divide and conquer strategies where, all right, I have this big array that I need to sort. I don't know how to do that. I'll split it into 2 arrays. And now this is a smaller array. Maybe that's an easier task. Right? Well, okay, I'll split that into 2 arrays and split that into 2 arrays, split that into 2 arrays, right? Using recursion, right? Until you get down to an array of size 1. Now what? Is there anything to do to sort it? By definition, an array of size 1 is sorted. Now the task is to simply just, if I have 2 sorted arrays, all I have to do is merge them together. Right? And so that's a divide and conquer strategy called merge sort. It's an algorithm called merge sort. And it is presented usually as recursive, and you can write it recursively, but you can also write it iteratively a lot better. Right? Now it's a little bit more complicated code, but now you're not abusing the call stack. Right? So you and I would definitely agree. If all things being equal, do not use recursion. In fact, there are, and we'll get to the disadvantages here after this demonstration, but there are style guides. For example, NASA forbids the use of recursion in their embedded systems because of the risks and because of the disadvantages. Right? If you overflow your stack, that kills your entire embedded system. Right? All right, so let's go ahead and see if we're right. Printf, Fibonacci fib of %d is equal to %. And I don't know, I forget what the placeholder is for a long. I think it's LD. We'll find out here in a second with the warnings turned on. Value, or n value. There we go. All right, so GCC. Well, here, GCC wall. Okay, hey, awesome. I remembered correctly. LD is the placeholder for printing a long digit. It's not long double. Right? All right, let's run that. 55. Excellent. Got it on my first try. But of course we should, in fact I'm going to go ahead and parameterize this so that's a to I of argv of 1, excuse me, so that I don't have to do this anymore. I don't have to recompile it. Let's just go ahead and compile it once and then provide it as a command line argument, 10. I still get 55. Now if I go up to 11, what should I get? What's next? 89. All right, and we didn't write it down, but if I went up to 12, what should I get? 55 plus 89 for you math majors is? I don't have enough figures. 144 looks good to me, right? Next one would be 89 and 49. That's too hard for me, too. 233. Yep, there we go. Excellent. Let's go down. What about a base case? 1 and 2 should give me 1. All right, making sure that the third one works. Making sure that other values work. Say 0. I should get a -1 here, and I should have done error handling. Right? I'm convinced that this actually works. Let's go ahead and try actually, let's go ahead and kick it off. I want to know what the 35th Fibonacci number is. Oh, okay, that was quite quick. Let's go with the 50th. All right, we'll let that simmer for a second. Right? And what is the 50th Fibonacci number? Right? We might be off by 1 here, by the way. Let's go ahead and check if we're off by 1. What's the 10th Fibonacci number? It'll probably say that it's 55. Okay, so are we in agreement? I think, okay. That was 10, right? Yeah. Okay. All right, we're in agreement here. So you tell me, Wolfram Alpha, when this gets done simmering, right? Watch pot never boils, that's why we're not watching it. Then what is the value? Oh, well, that's not that big. That's million, trillion, or billion. That's 12 billion, or no, that's only 12 million, right? 12 billion, there we go. 12 billion, which is definitely doable with a long, right? All right, Wolfram Alpha got that really, really quick. Okay. No. What do you mean no?
I don't know. Looks like it doesn't want to.
Well, it's still running. I mean, it's correct. That if we waited long enough, it would give me the correct answer. Ah, there we go. All right. 12, 5, 8, 6, ... Right? Yep, good. Okay. So let's go up to the 60th Fibonacci number. Right. Oh, did I what? Right. It will not overflow the stack. Don't worry about that, because the recursion depth will be at most 61 function calls, right? So we waited, what, a good 2 minutes maybe for the first answer? How long do you think we should wait for this answer? 3 minutes? Okay. I'm just going to go do some...
It's more exponential than that.
2 minutes times, it'll be 10 times as much, so 1.6 to the 10th. Can you do time math like that?
It's almost
2 times. Fine, we'll get that. There. Minutes. There's minutes. That's just a back of the hand calculation. Oh, somebody's playing Jeopardy. All right. So that's that many minutes. Right? How many minutes is that? 3 some hours, right? We'll get there eventually. No, we won't. If I wanted to go up to, say, even 100, right? This will take billions and billions and trillions and trillions and trillions of years. Trust me.
Only goes to
Right?
an hour.
You can do it. Is a loop faster? Or
A loop, well, yeah, that's what Wolfram Alpha is doing. Right? A loop would be instantaneous. Okay? So why is this so bad? Well, let's think about it. Right? And for that, I'm going to draw a pretty picture. Oh, it's not going to be that pretty. Right. Let's think about calling Fibonacci just simply of, say, 10. Right? So if I call Fibonacci of 10, that's going to be 2 recursive calls. One of them is going to be to Fibonacci of 9, and one of them is going to be to Fibonacci of 8. Right. Each one of those is going to be 2 recursive calls. 8 and 7 and 7 and 6. Right? I'm not going to write fib every single time now. This one is going to have 2 recursive calls to 7 and 6, 6 and 5, 6 and 5, 5 and 4. Right? 2 calls, 2 calls, 2 calls, 2 calls, 2 calls, 2 dot, 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 dot. Right? Now, just with this small picture here, how many times am I calling Fibonacci of 7? 1, 2, 3. Okay? Maybe I will draw it a little bit more. 6, 5, 5, 4, 5, 4, 4, 3, 5, 4, 4, 3. 5 goes to 4 and 3, 4 and 3, 3 and 2. Right? So how many times did we call Fibonacci of 7? We said 3. What about 6? How many times can you count those up here? 1, 2, 3, 4, 5. Predict. How many times would you end up calling Fibonacci of 5? 8. Whoa, how did you get that answer? It's the Fibonacci sequence itself, right? 4 would end up being, predict, 13 function calls. 3 would end up being 21 function calls, et cetera, et cetera, et cetera. Right? In other words, a lot of function calls. Why would you make the same function call 21 times? Just to make sure it's absolutely right, huh?
Error handling.
Error.
Error checking. Is recursion a good way to write test cases?
No, definitely not. Right? So I think that we wanted to go for 70. That would be that many function calls. What is that? Millions, billions, trillions, quadrillions, quintillions, sextillions, right? Now, if I gave you a very, very powerful computer, say a 1 teraflop computer, 10 times teraflops would be 9 operations per second, right? Seconds to years, right? However many, that would be 37,000 years just to do Fibonacci of 7 on a much powerful computer that I'm running this on right now, right? I think it's on Amazon Web Services, or maybe, probably not since it's a Microsoft product. It's probably running on Microsoft servers, and not to, belittle their servers, but it's definitely not that powerful. Right? It's not going to be teraflops of operations per second. Do we know what flops are? All right, flops is floating point operations per second. So, what is a floating point operation per second, right? That is a measure of a processor, right? How many floating point operations can you do per second? Anybody have like a 1080 Ti, 2080 Ti, 3080 Ti? 1080? Do you have a benchmark telling me how many flops it is? No? 2016? What do you have? Ah, okay. What have you ever benchmarked it?
1080.
Oh, okay.
1080 Ti has 11.3 teraflops.
Oh, okay. So 11.3 teraflops. Okay,
3080 Ti has 34.1.
34.1 times 10 to the 9th. All right, good. So with your 3080 Ti there, it's only 1,000 years or so instead of 37. Go ahead and get started on that. All right, no way am I going to even get this done within our lifetime. Right? So, so what's the solution here? Well, the real solution is not to use recursion, right? But maybe there's an approach here where we can have some sort of a hybrid solution here, okay? So let's talk about recursion in general, though. Recursion can be good, all right? It can be good in the quote-unquote good sense, right? Many divide and conquer style algorithms are presented as recursive, right? Because you can divide a problem into subproblems and conquer each one of those subproblems. And if it's the exact same solution over and over again, it's natural to want to call the same function over and over again on smaller and smaller problem sizes, right? It is a good way to think inductively, right? So you might eventually have a discrete math course where you have to do proofs and stuff like that. Induction, have you seen induction before, right? Where you have a statement that's true for k, and you want to prove the statement is true for all values. Right? You assume that it's correct for k, and you show that implies that it's correct for k plus 1. That's inductive thinking right there. That's recursion, basically, as a proof technique. Many functional programming languages encourage or discourage, I should say, discourage or don't even have loop control structures, right? And so, de facto, you're using recursion in those languages to get things done, right? Recursion can be simple, or clean, or mathematical, right? Or beautiful, right? That is easily understood. Right? And I would be absolutely in agreement that to a mathematical mind, to a mathematician, recursion absolutely makes sense. But that's not how real computers work. At the end of the day, a recursive function is still being run on a RISC or CISC or whatever architecture. It is still being run in a systematic manner of do instruction 1, then instruction 2, then instruction 3, right? It's that's an imperative style of programming. It is not the way most people even think, right? It's the way mathematicians think, but mathematicians by and large aren't programmers, right? I've met very, very few mathematicians, and my advisor included, that would be hard pressed to write a Hello World program, right? These things are all true, but they're also subjective, right? One person's beautiful code is another person's ugly code. Simple code, one person's simple is another person's complex, right? Clean or mathematical, that forces you to think of things in one particular style. So all the good that you can think of with respect to recursion, it's good in one sense, but all of those senses are subjective. The bad, however, is all objective, right? The recursion, when recursion goes wrong, it goes very, very wrong. Recursive functions are essentially abusing the call stack, right? And risk stack overflow. That risk is a very real, very objective measure for maybe you don't want to do something, right? You risk recomputing values over and over, like we are doing with the Fibonacci sequence, right? You risk an exponential amount of work, right? Which may not be feasible, right? I mean, computing the 70th Fibonacci number shouldn't be anything. That shouldn't be a big deal. It's not a big deal for Wolfram Alpha, but it's a big deal if you decide to do it recursively. All of these considerations are objective measures of why recursion is bad, right? And so I fall on that side of the fence. All things being equal, why are you doing this recursively? There are much better solutions, right? So how do you eliminate recursion? There are programming languages that don't support recursion at all, mostly old programming languages. I think that the early versions of Fortran didn't allow you to have a function that called another function. It's just because it's not a feature that they thought of, right? But otherwise, most programming languages do support it, right? But in general, any computable recursive function can be rewritten as an iterative function, with an iterative solution, I should say, with an iterative solution, right? What would it look like for Fibonacci? Let's not do it this way. Let's do it Fibonacci iterative. Right? So I am now living in a world in which I do have a loop. Well, first of all, we'll take care of the corner cases, the base cases separately, because there's no need to rewrite that code. Otherwise, let's go ahead and start out with a variable, right? Long value, previous is equal to 1, long current is equal to 1. Why did I have two variables there? Because I need to keep track of the two previous variables. Compute the next variable, right? Long next is equal to previous plus current, or current plus previous, current plus previous. That'll be my next value, 1 and 1. Now I need 1 plus 1, 2. Put that into a temporary variable. How much do I do that? Or how many times do I do that? There I'll just do a basic for loop, right? I'll start it out at 3 here, because if it was 1 or 2, then you'd already be done, right? I is less than or equal to n, I plus plus. Right? I will do this over and over and over again, right? The next one will be the current plus the previous, and then I need to make sure to set myself up for the next time. Let's draw a pretty picture of that. Right. Oops. All right. So if I've got the previous, the current, and I've taken these and I've added them into the next, I need to set myself up for the next iteration of this thing. In other words, I need to shift all of these values back. Right? So I need to put into previous the value current, right? And then I need to put into current the value next. That sets myself up for the next iteration. So previous is equal to current, current is equal to next. Previous is equal to current. I could get away with two variables, by the way, and a temporary variable, but I'll go ahead and do it this way, is equal to next. Right? That will set myself up for the next iteration. I do that for how many iterations? Well, I already did it for 1 and 2 as my base cases here. Otherwise, if it's 3, I will only do this once, getting the third value. If it's 4, I'll do this twice, getting the fourth value, et cetera, et cetera. And I simply need to return it after that for loop. Return, well, I guess it'll end up being in next, right? There we go. Long next. I don't do it over and over again. There we go. Now let's call this function instead of the recursive function. In our main, that is. All right. Now, what was 10? Just make sure I didn't break anything first. 55, still works. What was 11? 89, still works. 12, 144, still works. What didn't work before, or what took like 2 minutes? 50. Still works, and it's in a blink of an eye now. Right? A microsecond versus 2 minutes. Now, I'm not necessarily going to get the right answer here, but 60, instead of taking over 3 hours, or nearly closer to 4 hours by my estimate, we get an immediate answer here. I don't know if that's correct or not, though. We might be susceptible to overflow at this point. Right? If I go to up to 100, that would have taken billions and billions and trillions of years, we'll get an immediate answer. We'll get the wrong answer because of overflow, but at least we get the wrong answer quickly. Right? So, much, much better solution there. Right? Generally, you want in design, you do want to prefer a fast failure, right? If a system is going to fail, it should fail right away, as quick as possible. It shouldn't be, all right, well, this is a failure, and we'll go ahead and continue computing or continue operating for 5 hours or whatever, and then report the failure, right? Because it's been failing and causing problems for the next 5 hours. We want it to fail fast, right? Lots of mechanical devices are designed like that, that if there is a catastrophic failure, it fails immediately in a safe manner, like before takeoff or something like that. A helicopter might be designed to, if the rotors have failed, then it won't even bother taking off or something like that, right? It failed fast instead of failing in the air. Again, I don't know anything about motorcycle or helicopter design or whatever, right? All right, you can also use various tricks, right? I shouldn't even call them tricks, various techniques. Right? Tricks are bad, right? Yeah, tricks are for kids. Techniques are for us, adults, right? There are various techniques that you can take to eliminate recursion or to reduce its risks. Right? For example, you can use an in-memory stack. Right? Instead of abusing the call stack, create your own stack on the heap, and then you can abuse that all you want, right? Because it's much, much larger. You're not going to risk a stack overflow. You're just going to risk a heap overflow or an out-of-memory exception or an out-of-memory situation, right? You can use what's called tail recursion. Right? It allows a compiler to compile away the recursion and to reuse a stack frame. And the way that you do this is by simply not really having any local variables. And if a compiler can see that there are no local variables that need to be in the stack frame, and you're not using anything in the stack frame beyond the immediate value, it can go ahead and compile all of that away for you. And you end up reusing the same stack frame over and over and over again. Again, it's a compiler optimization. So whether or not you rely on that is, you're crossing your fingers and hoping that your compiler supports that. Or you can use, here I'll put it out on another block here. You can use memoization. That is not, again, it's not memorization. It's not me having a stroke or anything. It is memoization. I don't know where the word comes from, right? If you need to compute a value, go ahead and pay for the recursion. Right? So in other words, yeah, I need to compute this value. but I'm only going to compute it once. After computing it, the value, store it in a cache. Do we know what caches are? Or caches? Cache. What is it? It's a storage mechanism, right? A cache of weapons or a cache of food, right? It's where you store something. So in this case, you are storing something in memory. You are storing that value that you paid for to compute, right? The next time you need that value, you check the cache, right? If it has been computed before, you use it. Otherwise, again, pay for the recursion. This will help solve that tree that I drew, right? Instead of computing these over and over and over again, or computing, say, where's my pen? Instead of computing Fibonacci of 3 21 times, we compute it once and put it into a table, into a cache. And then we don't have to recompute all these values here, right? If we've computed Fibonacci of 9, for example, or let's say 8 over here, for example, I don't need to recompute it over here. Guess what that eliminates? This entire tree. Half of my computations have been eliminated with just one function call. Right? Instead of computing Fibonacci of 7 twice, I will go ahead and compute it once, right? And that eliminates this branch of the tree. And this is a tree, right? I'm pruning it, right? We call that pruning trees. Eventually I'm going to prune this down so that that everything is computed exactly once, right? If you prune down a tree so that it's only one thing, is it a tree anymore? Yes, but now it's just the trunk, right? It's just a stick now, exactly, right? You've pruned every single branch, and you only have the base. Now, you don't want to do that to a real tree, but you certainly want to do that to a computation tree, because the fewer branches there are, the more that you cut out, the more that you prune out, the faster your computation time is going to be. Right? So, as an example, I'm going to go ahead and rename this Fibonacci recursive. Right? There we go. Let's start over and use memoization here. Okay? For that idea, I'm going to still return a long here. And I'm going to call this Fibonacci. Since I renamed the other one, I'm just going to call this Fibonacci. Right? I'm still going to take n, but I'm also going to take a table of values. Well, a table in this case is an array of long values. Right? And I'll call it values, because I don't know of any other name to call it. Right? Pre-computed values. And now what we're going to do is we're going to check. Well, if n is less than or equal to 0, then we'll do the same thing that we did before. That's just our corner case. That's our error handling, right? Then we'll go ahead and return -1, right? Else if, now what we're going to do is we're going to check, right? I'll put it over here. Right? Check the cache. In fact, that's what I'll call it. Not values, cache. Spell it right. Okay? Check the cache. If the value of Fibonacci, fib of n, is in the cache, ... then you just return it. Right. Else, pay for the recursion, but also store the value, ... Right? Now, that's just my pseudocode way of writing this. What we need to do is we need to come up with a way in C for that to have a meaningful statement here. So if the value of fib is in the cache, right, cache of n is valid, ... Right? Help me out. How do I know if it's a valid value or not? I could put in a bunch of invalid values. What's an invalid value? 0 or -1 or whatever, right? So if it's valid, then that would mean that it's not 0. Right? So, note to self. Fill the cache with invalid values initially. Right? Invalid values, that is zeros initially. Okay? And if it's not equal to 0, or maybe let's change these. Check the cache. If it is invalid, and if it is an invalid value, 0, then compute it. Then 1, pay for the recursion and compute it. But then 2, store it in the cache for future function calls. ... Right, there we go. Otherwise, we'll return it. Well, what is returning it? If it's not 0, then I'll return cache sub n. Okay? If it's an invalid value, then 1, pay for the recursion and compute it. That's going to be this thing up here, right? And I should rename this, right? Fibonacci recursive, Fibonacci recursive. There we go. In other words, I'm going to make a recursive call to Fibonacci, right? And we'll go ahead and go with long previous is equal to Fibonacci of n minus 1, right? Long previous previous, I don't like that. Previous last, say what?
Previous again.
Previous again. Okay. That's the one time I would forgive a variable like that. Or let's see, we could go A and B, previous and so there's last, second last, no. Penultimate.
Not previous.
Not previous. All right, fine. Remember, there are only 2 hard things in computer science. What? Cache invalidation. Hey, we're doing cache invalidation. No, that's not the same thing. Or naming things, right? Is equal to Fibonacci of n minus 2. But I don't want to call that other Fibonacci. I want to call this Fibonacci. And I'm going to pass in the cache to see whether or not it is in the cache, right? I'll ask the recursion, is n minus 2 in the cache? If so, then you return it to me and you don't actually do any more recursion, okay? I've stored, now I need to store those 2 things, right? I'm going to have long value is equal to previous plus previous 2, previous 1 plus previous 2, right? That's the value that I'm ultimately going to return, right? I want to store it in the cache for future function calls, though. Right? So cache of n is equal to value. Right? And then we return it, return value. Okay? Now we could probably simplify this greatly because we set cache of n and we immediately return cache of n. We do that again right here. So you could go ahead and cut this code down. I'll leave that as an exercise to you. I'm going to keep it as is because it's a little bit more descriptive for demonstration purposes. Right? Otherwise, what I would do is one single long value here, initialize it to -1, and change this so that there's no condition here. Change this and just return the value then. Right? But I'm not going to simplify it that much. Right? All right, so instead of calling Fibonacci iterative, we're going to call Fibonacci of n with a cache. Now, I need to set up my cache in order to pass it on to this and use this memoization function. Right? Long star cache is equal to, I need to make a call to malloc. How big should it be? Well, first of all, what's the return value? How should I cast that? Long star. Right? And if this were an integer, I would say malloc size of int. It's not an integer, it's a what? Long. Size of long. Right? And those are 64 bits instead of 32 bits. And how many of them do you want? N. N? Normally, yes. Remember how we started Fibonacci, though? At 1. So unless I want to shift all my indices to account for the 0 index, I'm going to cheat and go 1 extra. Plus 1. Right? Now, if I want to compute the 10th Fibonacci number, that means I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 right, as indices, and I'm ignoring the 0th index. It's just a little trick. Right? Technique. There we go. Now I need to fill the cache with invalid values. ... How do I do that? a simple for loop. For int I equals 0, I is less than or equal to n, because I do want to go all the way to the end, I plus plus. Cache of I will be equal to -1 we decided, or no, we said 0, 0. -1 would have been fine too. Okay. And then call Fibonacci on that. GCC. It should still work with, say, 10. Oops. Darn it. What's wrong? Oh, I know what's wrong. So, what happened? I filled it with invalid values. I took care of the error base case. What happened to my other two base cases, though? What are my other two base cases for Fibonacci? When n is 1, n is 2. Do you see those accounted for here at all? So you can either write an else statement here to account for it, or what can you do to the cache? Fill it with invalid values, except for, now set the base cases, ... Cache of 1 is going to be 1. Cache of 2 is going to be 1. Right. There we go. And run this. There we go. Now it's 55. That was correct, right? 11 should be 89. 12 should be 144. 50 will probably be instantaneous, and also, you know, it's recursive, but we're using memoization, caching, in order to avoid repeatedly recomputing the same value over and over and over again. Right? What about 100? Again, we'll get the wrong answer, but we'll get it quickly. Right? I don't know. Will we get the wrong answer? 100th Fibonacci number. That says 354224. Yeah, it's wrong now. It's definitely wrong. Right. Overflow. Anybody want to know what we do if we want? Again, this is a toy example. Why would you ever be computing this stuff in real life anyway? What are your suggestions for computing the 1000th Fibonacci number that is probably going to have hundreds and hundreds of digits?
You import a type called extra long.
Extra long.
Really big.
Longer. Yes, but then eventually you'll get to a point where you've got a maximum on that too. If you've got a finite number of bytes, then you've got a finite representation of numbers. You need what's called a multi-precision library. And the one for C is going to be GMP, which is GNU's multi-precision library. And that one you can represent arbitrarily large numbers, or you can represent, say, pi out to 1 billion digits or something like that. The way that it works is, in software, if you need more bytes to represent something, it dynamically allocates more bytes. So instead of having 32 bits, 32 bits, 32 bits, you have all of these bits representing a very, very large number. And if you have overflow, it allocates a new memory space that's even bigger, that you can have more bits for it. In fact, that's on the, if we go to your hack for next time. No, I'd have to pull up the PDF. It suggests that as an advanced activity, you can go ahead and pull in GMP, GIMP, GNU's multi-precision library, and compile it with that and get an arbitrarily large number. So you can compute, using memoization, of course, or iteration, you can compute the 1000th Fibonacci number accurately, if you really want to. Libraries like that are not niche libraries. They're absolutely essential if you're going to do anything with large numbers, with very, very precise numbers, or say with cryptography or something like that, where you've got numbers that are, usually 4,000 bits or something like that. Right? You've got keys that are 4,000 bits. Okay. All right. Questions on memoization? Again, I don't know where the term came from. All right, then you don't have Hack 12 this Friday, but just as a really quick preview, I want to make sure that we have at least some math background for it. Because you're not doing the Fibonacci numbers, you are doing, come on. you are doing the binomial coefficients. And so what does that look like? Let me reformat this stuff. There we go. N, how do you read that thing right there? I guess it's right there. N, choose K. You've probably seen this before, maybe in high school math, maybe? Yes, no, permutations, combinations, all right, maybe not. In any case, you just have to compute the math anyway. The good way of computing this, N choose K, that corresponds to the number of ways of choosing K elements from a set of size N. So for example, let's go ahead and draw another pretty picture here. If I've got, say, A, B, and C, and D, how many ways are there of choosing two of these things? I could choose A and B, or I could choose A and C, or I could choose A and D. What about BA? That's already chosen, that's the same thing. With combination, order does not matter. Permutations, the way of arranging things, order matters, okay? So this is the same thing as AB. What's another option? Don't choose A, choose B and then something else. B, C, B, D. Don't choose B, don't choose A, C, and D. How many of them are there? 6. That corresponds to the 4 original elements, and you choose 2 of them. That's 6. When you plug that into that that thing right there, then you get 6. Oh, before I say it, what is that exclamation point? Factorial, right? N minus k factorial, which is going to be 4 minus 2 factorial, and 2 factorial. Right? You compute that, and you get 6 again. That would be combinations, combos with repetition. That is going to be well, yeah, I mean, how do you, if it's like, say, 4 elements, A, B, C, and D, A, B, it would be permutations. I don't remember the formula off the top of my head, but it would be permutations with repetition divided by combinations with repetition. Something like that. Right? And then you get in, that's all combinatorics, and then it might even be a Stirling number of the second kind. I'm not sure, I don't remember. Don't worry about it though. Keep it simple, right? This is the only combinations you need. Now sometimes you've seen this on your calculators and there's like an NCR or an NCK or something like that, or CNK or CNR or something. That's going to be the exact same thing here. Right? You can compute it with factorials, or you can compute it using this thing right here. Does anybody know what this thing is? We're talking about Sierpinski triangles. This goes into something else. Pascal's triangle. This is Pascal's identity right here. Right? Has anybody seen Pascal's triangle? Right. There we go. It looks, what's the prettiest one? Nice rainbow one. There we go. That is how you build Pascal's triangle using Pascal's identity. What value 6 is? 6 is the value that I computed before, right? How did we get that value? 3 plus 3 is 6. How do we get 84? 28 plus 56. So the value right below is simply just the 2 right above it. So this tells you how you could use memoization by simply filling out a table of Pascal's triangle values. Right? If you want to compute this very, very large number here, all you have to do is compute all these numbers up here that lead to that number. And that's what Pascal's identity gives you here. Right? It's the number of ways of choosing k elements from a set of size n. Right? It comes up all the time in binomial distributions. They're the binomial coefficients. So if you have a binomial that is, again, more math. You're engineers. It's definitely math, right? Engineers and trade. Binomial coefficients. If you've got x plus y raised to, say, the 20th, right? If you were to expand that out First of all, you'd get a hand cramp very, very quickly. But you would have a whole bunch of combinations of x's and y's, and all of the coefficients sitting out front of out front of those would be the binomial coefficients. Right? I don't want to write that. Wolfram Alpha, can you do it? Give me the expansion of x plus y raised to the 20th. There we go. 20, 19, all of those coefficients there correspond to the binomial coefficients. Let's keep it small. Let's keep it to the 5th. And that'll look somewhat familiar. 1, 5, 10, 10, 5, 1. 1, 5, 10, 10, 5, 1. Right there. So combinatoric stuff shows up all the time. Think of one combinatoric thing like n choose k, and you've got like 100 different interpretations or applications of that stuff. Right? Binomial coefficient, binomial distribution, Pascal's triangle, right? Et cetera, et cetera. What you'll be doing in your hack, not this Friday, but the next Friday, will be implementing a memoization that computes this stuff, right? Instead of relying on the recursion. You rely on the recursion, it will take you thousands and thousands of years. Got time. Any questions? No? All right. Then in your hack 11 this Friday is a focus on structures and encapsulation. I think that you'll be building, yeah, we already previewed it last time, right? That you'll be building a structure to support airports and then computing air distance between the airports, which you've done before using latitude and longitude, right? That's after lab. Lab, I think you do RSS feeds. And if one of the RSS feeds is not working, let me know, and you can go to any RSS feed that you want. I think that the Reddit one will always work. Right? But don't, let me know if they're not working. The UNL has changed their RSS feeds over the years, and sometimes they break. All right?